Alright, so this will be our final video on limits for Math 1560 at the U of L for fall 2017. And in this video we're going to look at one really important consequence of continuity called the intermediate value theorem. This is a theorem that is actually it's a very obvious, it seems like a very obvious result, but it's in fact quite difficult to prove. This statement looks a little bit intimidating, but let me kind of sketch out what this is telling you. So what it's telling you is you've got a function, and it's continuous on some interval. Let's say it's continuous from A to B. And we suppose that at one end of the interval, it's negative. And at the other end of the interval, it's positive. All right? Now, if it's a continuous function, we know intuitively that continuity means that we can't have any gaps or breaks or anything like that in our graph. The graph should be one solid piece. So what the intermediate value theorem says that if you've got a continuous function, there's no way that you can get from below the x-axis to above the x-axis without crossing the x-axis, right? We're not allowed to jump over the x-axis because if we jumped, we would have a break in our graph, we would have a discontinuity. All right, so any attempt that I make is going to force me at some point to cross. Now I might cross at more than one point, but I do have to cross at least one point. So that's my C. So that's what the intermediate value theorem is saying, right? That if you start below and you end above, at some point you have to cross the axis. And of course you could do it the other way around, where you're above at the left end and you're below at the right end. Whether you go from negative to positive or positive to negative, it's the same story either way. And by the way, the intermediate value theorem is why sign diagrams work. This is why we know when we plot out those sign diagrams for polynomials and for rational functions, we know that the only place where a sign change can happen is at either a zero, like this, or at an asymptote. And notice that those vertical asymptotes, right, those are points of discontinuity, right? So once we know all the zeros and we know all the asymptotes and we know all the discontinuities, we know all the places where possibly that function might change from positive to negative. And that's why we only have to kind of work out the sign in between each of those points, right? We know that between any two such points, the sign has to remain constant. It must be all positive or all negative until you get to one of these points where you have a potential sign change. This is maybe not the most general version of the intermediate value theorem. You could also state the intermediate value theorem so that instead of 0 being kind of the point of interest, you have some other y value, so you kind of shift things up or down. But the 0 version tends to be most useful in practice. And you can do sort of things like this. You can say, okay, here's a kind of consequence. Here's a little theorem that I can prove using the intermediate value theorem. The square root of 2 is a real number. Okay, seems silly. We take this for granted. Of course, the square root of 2 is a real number. But why do we kind of, why do we know this is true? Well, basically, what is the square root of 2? Square root of 2 is a 0 of this polynomial, x squared minus 2. So take that to be my function. In the last video, we pointed out that every polynomial function is continuous. So if I can guarantee that this function has a 0, then I know that 0 has to be a real number. We're working over the real numbers here. Then I can say that root 2 is a 0. So why do I know that there has to be a 0 for this? And by the way, the other 0 was minus root 2. But how do I know that that must be, that I must have that 0? Well, if I consider, let's say, x equals 0, I notice that f of 0 is equal to minus 2 is less than 0. If I did f of, let's say, 2, that would give me 2 squared minus 2. 4 minus 2 is 2. Bigger than 0, right? So now I know there has to be a positive square root, because somewhere between 0 and 2, my function has to cross the x-axis, I have to have that 0. And basically you would define the square root of 2 to be the positive 0 of this polynomial. That's, this seems silly, but it's the sort of thing you could do depending on how kind of technical and pedantic you want to be about your real number system. And one other thing that I should probably mention, like I said, the proof is really, really hard. We're not going to go anywhere near it. And the reason we don't go anywhere near is the proof really gets to the heart of the definition of the real number system, what it really means to be a real number. It gets into some very technical properties that just aren't appropriate for a course like Math 1560. It's something that you might discuss if you go on and you take Math 3500. Okay, so now, in the silly example I gave you on the last slide, right? I mean, it seems silly because we know what the square root of 2 is, and so we sort of already know how to find the zeros for that function. Here's a cubic, right? X cubed plus x plus 1. How can I prove that this thing has a 0, right? How can I guarantee that it has a 0? Well, what I can do is I look at it like this. I say, okay, here's a proof. Okay, if I calculate f at minus 1, I get minus 1 cubed plus minus 1 plus 1. This comes out to be minus 1, which is negative. If I calculate f of 1 at the other end of my interval, I get 1 cubed plus 1 plus 1. Okay, I get 3, which is positive. Okay, so now I know that it's negative at minus 1. I know it's positive at plus 1, and of course it's a polynomial, and every polynomial is continuous. So since f is continuous, we know that f of c equals 0 for some c between minus 1 and 1. By the intermediate value theorem. And the reason that this is significant is that this is not a polynomial with rational roots, right? The only possible rational roots for this polynomial are actually minus 1 or 1, and we see that those don't work. Those don't give us a 0, right? So there is a real number that makes this function 0 between minus 1 and 1, but it's going to involve roots, maybe cube roots, maybe square roots. There's going to be some, it's not something that we can solve for algebraically. It's going to be a huge mess if we tried to do it. So the best we can really hope to do is to try and approximate that 0. Now, by the way, I know some of you, if you've done your reading on Wikipedia, you might know that actually there is a formula that you can use to get zeros of a cubic. But if you've ever seen it, feel free to look that up. Feel free to look up a formula for the zeros of a cubic, right? Like, the quadratic formula. There actually is a cubic formula, but you'll take one look at it and decide that you never ever want to see it again. It's not a nice thing. Okay. So how can I get an idea of what that number is, right? This is the problem with the intermediate value theorem. It tells you that number exists, but that's all it tells you. It doesn't tell you what it is. All it says is, I know that number's out there. Somewhere between minus 1 and 1, we have this number. Who knows what it is, but it's there. How can you kind of narrow down the value? Well, one of the things you can do, there's a trick you can use called bisection. So what you do with bisection, right, so our function, just to remind ourselves, our function is x cubed plus x plus 1. The way bisection works, and this is something that really you should use a computer for, maybe a spreadsheet or something. We'll just do the first couple steps to give you an idea of how it would go, is we say, okay, somewhere in between these two, we know there's a 0. Let's see what happens halfway in between. So we kind of always go halfway. So the first thing we do is we check 0. Okay, because that's halfway between minus 1 and 1. F of 0 equals 1 is positive. And remember, we knew that f of minus 1 is negative, right? So it's already positive at 0. That means now that sign change we're looking for, that switch from positive to negative, it's not happening between 0 and 1. It's happening between minus 1 and 0. So now we know that C is between -1 and 0. And now we divide in half again. So we check the midpoint here. So we check x equals -1/2. So f of -1/2. Here's where you start wishing you had a calculator or a computer. We get -1/8 minus 1/2 plus 1. Now that is -1. Let's put everything over 8. 1/2 is 4/8. Minus 4/8. 1 is 8/8. Okay. I get 3/8. Okay. Which is still positive. And that means that we know that C is somewhere between -1 and -1/2. So what do? Well, we cut this in half again. What's halfway between -1 and -1/2? We check x equals -3/4, right? And so we do f of -3/4, and okay, this is starting to get a little bit crazy here. 27/64 minus 3/4 plus 1. And okay, can I do this? Over 64 minus 27. 3 times 16 is 48. Plus 1. Oh, plus 64, right? Over 64. And oh, what do I get now? This is now going to be negative, right? That's 68, 75, minus 75 plus 64. I get like minus 11/64. Okay, so now at -3/4, I know that it's negative, and so that means that, just as well, let's kind of put it in here in red so we can see it. So this means that C is in, well, now we know it's between -3/4 and -1/2. And then we could keep it going. We could check in between -3/4 and -1/2 and see whether we're positive or negative there, and we keep chopping the interval in half. And and the length of that interval gets pretty short pretty quickly as you keep chopping it in half. So you can narrow things down. You can get as precise as you want, but you can see that if you want to keep iterating this, you don't want to do this by hand. You'd want to use a computer. Okay, that's it for continuity. In the next video, we're going to start derivatives.